I often travel in disguise, so I have this slide stack that's L42.org that should take you to a link to the PDF. There's a whole bunch of shortened links throughout for references to material. If you don't recognize me, one of my other forms may be more familiar. Hair grows fast and it's fun. As Kurt said, I've been doing this for about 20 years. I pursued my PhD at Johns Hopkins in the Center for Networking and Distributed Systems. I left there and hoped to never have to troubleshoot and debug distributed systems again, and ended up here somehow, debugging and troubleshooting distributed systems. So that was ineffective. So running away from things in life is not always the right answer. You might end up right back where you started. So one of the really interesting things that I've noticed over my time in computing is that all of the theoretical problems and all the problems that kept me up at night during my PhD studies, they've come back in ways that are more prevalent to the average practitioner today. Because we've made bad life decisions as an industry. So this talk kind of takes us through a tour of how we got there and why it matters. So in the beginning, anybody here install software this way? Yeah, right. Anybody here install software off of tape? There we go. All right. So online updates were not really a thing at that point. So we developed software very differently at that point in time, right? So we built software. I'd like to say we tested it a lot, which is probably not any more true than it is today. But we shipped it, it was installed, and it ran largely disconnected. So even the online software that we wrote, the software itself used internet connectivity or dial-up connectivity to do the things the software did, but not to change the way the software worked, right? So we weren't doing online updates. It wasn't changing the software state based on online data. It was talking to someone or pulling an inventory list or something like that. So the way that we distributed software and the way that software interacted with other software was fundamentally disconnected. And then things got connected. So what was really interesting when things got connected, though, is that we didn't change the way we built software in a lot of ways. We built software, we distributed it, and it ran largely undistributed. So either we shipped a thick client to someone, and then we used the internet to do software updates or distribute that software, or we shipped a really thin client and did all of the work on the server side. And I bold the server because back in 1995, 2000, the vast majority of sites, most of the logic was actually on the server. It wasn't on the servers. It was on one. I mean, you could service 100,000 users on a single server, and there weren't that many sites that had more than 100,000 users in that time era. So it didn't really require thinking about these problems in a way that was distributed. And that's probably a really good thing, because I think that if it would have broken us as people to have adopted the internet, adopted global scale, and adopted distributed systems all at the same time, I think we would have all left broken people. So really the distributed applications of that time were kind of few and far between. The web with its kind of MVC look, when the view was in the web and the model and the controller were on the server side, it still wasn't all that distributed. Nowadays, when you have apps that can run on the server side or in the browser or hybrid or both, and the user doesn't even really know, depending on how slow their connection is, it kind of changes. That's really interesting, right? Now you're actually having multiple computers do work and the user doesn't even really know it. Point of sales applications actually had this challenge all the time. You have inventory in a warehouse and you've got inventory in a store and they have to synchronize, and you've got some horrible dial-up modem that connects them. And when they're not synchronized, you sell something you don't have. These problems were real, so people had to struggle with those. In a lot of ways, the Basho company, React, like a lot of that was born out of experience and point of sales related stuff. And then the other thing that was really common at the time, at least maybe it was more common where I was HPC. So I live right near 3 agencies that all have 3 letters, right near Washington, D.C., which is, I would say, the tire fire of our moral crisis in the United States right now. Everything there was high-performance compute. So everything was the Beowulf clusters of the time where you had 50 machines all trying to get a job done just a little bit faster. And that was, it was interesting because it was coordinated progress. So all of those things, it wasn't like they were trying to figure out what work to do. They were all just doing the work given to them. So in high-performance computing, it was really about centralized decisions about distributed work. And that distributed work was highly uncoordinated. So that was actually really simple sorts of problems. These were not the hard problems of distributed systems that we even face today. Those are a little different. So the reason that they're very, very different is that when you have, so everyone here that has consumers visiting a web property has a distributed system. If you're shipping JavaScript to a web browser and you have 10 million people visiting your site, you actually have 10 million nodes you are running code on. So you have a very large distributed system to deal with. The beauty of that distributed system and why it's so easy to reason about is because when that node breaks, it affects exactly one user. It's the user using that browser on their computer, and that's it. So there are some interesting new technologies out there. There's a new CDN tech called Edge Mesh, which actually leverages like P2P WebRTC in people's browsers to power peer browser sessions. So now things get really weird because when you have a node fail because somebody malfunctions, somebody's computer malfunctions, it blue screens, it panics, or they just unplug it, it now can affect a peer user, which is a much more interesting problem. That's recent. The ability to have a node in a distributed system fail and affect more than one user, we actually brought that problem on ourselves by creating distributed backends. So this is a kind of hard ratio to understand, but the reason everything changed is because if you look at the ratio of affected users to node failures, if there are a few users that are affected by a lot of node failures, it's a very, very difficult problem to reason about. So, and if you have just one node failure and many, many affected users, it's actually really easy to reason about, right? So if I break my site and no one works, it's like it's broken. This is pretty easy. If I fix it, it starts working again. If I have 10 million users and 1,000 of them are having an odd experience because one of my systems or a few of my systems have stopped working together cooperatively, it's a very, very difficult problem to debug and understand. So I'm going to take us through some things that I think that everyone should learn about distributed systems. I was hoping to not have to have that conversation with anyone ever. It's kind of like a parent where you're dreading that conversation. And it's like, hey, well, if people just don't breed ever again, I don't have to have that conversation. When I was in distributed systems research, it was like, I don't ever want to have this conversation again. I don't want to teach this to anyone. We should just not have distributed systems. But it turns out that we've done this to ourselves, and there's some important life lessons that need to happen. So I think that distributed system failure through poetry is a beautiful thing. DNS is one of those distributed systems out there that is the most prevalent in the world. It is a truly distributed system, and it almost always works. It's kind of amazing. It's one of those things, I don't know if you're ever sitting at a computer and then suddenly you're like, you have one of those breaking moments where you just want to scream at your screen, or you freak out, you're typing along, you're editing in VI or Emacs, and you're compiling code or whatever, and you're like, oh my God, I don't understand why any of this works. Like the whole system, I just sent a UDP packet which shouldn't have gotten somewhere because if you've ever looked at routing systems, it's amazing those work. And I've kind of just thrown this like paper airplane of a packet somewhere, and I got an answer back in like 8 milliseconds. and it's right. And it's like, and I had to do that like 15,000 times without an error over the last workday. And I never got an error back. Like, it never really screwed up. I don't understand how this works. Like, and my code doesn't work. Like, what the hell? Which is why, when there is a DNS problem, we are in such vehement denial of it being a DNS problem, because it just tends to work. But when it doesn't work, man, it is your worst day ever. So talking about the progression of understanding of systems, I think we all learn when we first start programming or operating systems or debugging systems, we start in a single user, single system context. This is, I have an algorithm to sort an array of integers and it didn't sort it right, how do I debug it? You don't start with, I have an algorithm distributed across 10,000 nodes sorting an arbitrary number of arrays, and some of them are not sorted correctly, debug it. That's not how you start things. So as a junior programmer, or especially in an educational system, vocational or otherwise, you really start in like procedural programming land or functional programming land with one thread, with one process, with one input and one output, and you work through it mentally. And some people are good at that and some people aren't. I think it's not, the same people who are good at putting puzzles together are good at debugging. And it's interesting. Some people are good at putting puzzles together. Some people look at puzzles and go, that should really come pre-assembled. This is uninteresting to me. But debugging is a lot like puzzles. So the next thing that's really important that we learned as an industry is how to do distributed users, but we still did single systems. So there's one architecture, there's one database, there's a couple of web servers that didn't have state, and there are thousands or tens of thousands or hundreds of thousands of users, and we have to debug why their sessions don't work. And this was somewhat easy to understand. And then in 2000, I think this was the real problem where we had a mental gap where we all stumbled. We could no longer serve our audiences with single systems. It just doesn't work. You don't have one database anymore. You can't handle 10 million users with a single database usually. So you end up building more complex systems. Microservices is one answer to this. Everything that's old and is new again. It's like unspecified SOA in a lot of ways. But microservices in a lot of ways are our answer to I don't want a database at all. I just really want a service, and its implementation details should be left to a team. But we couldn't think about both distributed systems in the back end and distributed users at the same time, because I just think our minds would melt. We didn't have the right tooling, we didn't have the right wherewithal. People don't understand enough distributed systems theory to really troubleshoot that. So what we did is we didn't look at groups of users as a whole. We just used individual users. This user has a problem. Let me trace this individual user's bad experience through the system and try to understand what the pathology of the pathological problem in the system that caused this individual user's experience to be bad. But now, or even in 2005, I think we had to bite the bullet and understand that those problems are highly complex. And the rise of social interactions in applications really changed that. You can't describe a single user's bad experience because that single user is interacting with another user on your service. And that user can have a different failure mode because they are touching different parts of different systems. So the way we deliver our applications, the expectations of our users and how they interact with our applications have changed it so that we no longer have an easy way out. You have distributed users that interact with each other through your applications, and you have distributed servers and services on the back end providing those things. So we are fucked. That's just how it works, and we have to have the tooling around that. And a lot of the tooling is not technical tooling, it's brain tooling to think about these problems. So, and when you think, okay, screw it, I'm just gonna become like an iPhone developer. I don't have to worry about this would be great. Your iPhone has like 8 different processors in it that all have different clock speeds. Right? You have a completely distributed system in your pocket. And brilliantly through the OS, they have abstracted away a lot of the mechanics and distributed systems reasoning that you need to program a mobile device, an Android or an iPhone successfully, but it is still there. And as we start to extract more power out of those by using things like GPUs in the phones to power our ML or whatever it is, we are going to run into those things again when you realize that like the GPU does things at different speeds than your processor and your expectations are no longer met. So what are the things that we need to remember in distributed systems? So this is kind of a book of things that are important. The first thing in distributed systems is that you have to have an understanding of time. And this is probably the single hardest thing to think about. But if you have a clock, you know what time it is. If you have more than one clock, you will never, ever know what time it is. They don't agree. You don't know which one's right. If they don't agree, which one do you choose? Did everyone agree to look at the right clock and not the left clock? You have a very, very big problem. I wrote an article about taking time measurements in computers for the ACM. I was in the communications of the ACM last year. And one of the things is it's all around Alice in Wonderland pictures. And the rabbit is holding his stopwatch here, and he's looking at it. And you think about, okay, you have one clock and you know what time it is, right? How long does it take light to travel from the hands of the clock to your eyes? It's really interesting. At this distance, it takes 1 nanosecond, which is 3 instructions. You've already done 3 things on a computer, right? So if you look at a clock tick rate on systems, it's like 2.5 to 3 instructions per nanosecond, cycles per nanosecond that you get out of that. That's crazy, right? Like you literally don't know what time it is. When you look at what time it is, you have observational bias of having looked at the time on a system, and you have the delay of actually assessing the time. So one, even on a given system, you really don't know what time it is. When you have 2 systems and you try to think you can sync their clocks, remember when you're talking about race conditions in programming, anybody's ever had a threaded race condition? Anybody? All right. You're in the same box on that. When you're on a distributed system and you think you have the same clocks, which you sort of do in a single system, but when you have multiple systems, you have separate physical clocks, and there are no way that they are instruction cycle level aligned. So one of my hopes is that 15 years from now, people look back and you remember, and they say, "Do you remember when people didn't have a single clock in a distributed system? Oh, that must have been really hard," right? So I'm hopeful that when people say all this like quantum entanglement and doing all these qubits and things I just want a fucking clock that works, right? So if I had a clock and I quantum entangled all the clocks in all of my systems around and they all ticked at the same rate, magic would happen in the industry. We would have Spanner would be accessible to every single person who bought a computer. Right? That's one of the reasons that Spanner was so hard to write, was that you have to actually have synchronized time across lots of machines. That's expensive. If it becomes built in, like my watch has something, I have a microchip embedded in my hand that has a clock, and every computer I touch automatically is synchronized to the femtosecond to my that would be awesome. That'd be great. That doesn't happen. That is not available today. Maybe it'll be available after I retire. I don't know. So when you think about clocks in computers, you cannot use wall clocks. Nanoseconds don't matter. Femtoseconds don't matter. They matter for timing things. They don't matter for order of events. So this is the most important thing in distributed systems, is that clocks and time are not used for timing things. They're used for figuring out what happened before what else happened. It's the concept of A happened before B. Those are the things that we need to know. Right? So there are 3 types of clocks. I'll get into that. But we have to think about causality. So as these things happen, this is from Wikipedia, I think. There's a link to it as well. As things happen on these systems, we're sharing this logical progression of time. So in the slide before, Leslie Lamport, who won the ACM Turing Award last year, it's the most prestigious award in our industry. He won it for a variety of things, and it wasn't creating LaTeX. But Lamport timestamps are the one brilliant insight that he had that changed the way we thought about distributed systems. He basically said, I've got this clock, and it's just a number. It's a register, effectively. And every time I do something, I'm just going to add 1 to it. Guess what I get? I get a clock that always goes up. By the way, physical clocks can go backwards too. It's horrible. Logical clocks, you're just moving it forward all the time. And if I say, hey, I'm going to take my clock and I'm going to do something and move it forward, and I'm going to give you the result of that computation with that new clock counter, and you take that clock counter and you say, oh, I'm going to do some work too. I'm going to add 1 to my clock counter, and I'll take the maximum of those 2. And then I'm going to bundle up my result and hand you back that new clock counter. And that clock counter starts to move forward. There are a lot of things that happen in that system where you don't know whether they happened A before B. But there are certain things, once I've gotten that counter back and I've produced something and handed it to you, when I see a counter that is ahead of the one that I last produced, I know that it happened before the things that I did before. So it allows us to have this idea of causality. I know that certain events, and cause and effect and causality doesn't mean that they caused them. It means that they could have caused them, right? So the important thing there is that there is nothing in that effect window that could possibly have caused the cause window. They happened afterwards. And in distributed systems, when these things are nanoseconds apart, this mentality, like understanding how progression happens, is critically important to troubleshooting. So causal thinking is hard because unlike debugging where you get like an unordered array and you're looking at your algorithm and trying to think, how did I get here? In distributed systems, every single system state everywhere is a potential way you got to where you are. So understanding causal thinking is incredibly important. Another thing that's really important is that remembering that one person's failure is like a Byzantine tragedy in distributed systems. And they tend to be around timing. So this is a failed circuit breaker. If anybody knows the circuit breaker pattern, this causes burned down houses. It's not what you thought a circuit breaker was supposed to do. But a lot of timing failures in distributed systems, a lot of failures, pathological failures in distributed systems are around timing. Imagine 2 people, a train coming into one station every 10 minutes and a train leaving that station every 10 minutes, right? And almost everyone, they take train A and then they switch trains, they transfer and get on train B, right? So what's the average time that you're going to be in the station? Well, math person would say, well, they arrive every 10 minutes, so the worst case is 10 minutes, the best case is 0 minutes, it's probably about 5. It's probably not about 5. It probably has 1 mode, and it's probably 9 minutes, and it sucks, right? Because they run them at the same time. You get off your train, you just miss the other one, and then you have to wait 9 minutes for the train to come back around. These types of timeouts trigger in distributed systems all the time where the timeouts align, and you get worst case pathologies all the time. Another thing that's absolutely important is to understand consensus. Paxos is hard. It's one of the things that Leslie Lamport also did. Raft is much easier to understand. And for something completely different that uses concept of Lamport timestamps and vector clocks, view synchrony is a different method of kind of agreeing about the order of things. And these are the technologies that distributed databases are built upon. These are how decisions are made. And when an unthinkable decision happens, you have to be able to troubleshoot it. And this is like, I don't know, this is probably a recommended architecture for a blog these days, right? I have no idea what it is. And now I have all of these problems, right? So you have to ask yourself, is it worth it? So what do we get out of this? What do we get by making all of our systems distributed? We get modular development. We get language domains, right? So I can choose a different language for a different problem because I have all of my components separated out and talking over the network. I get separate security domains. This is pretty neat. Different availability domains, different resiliency domains. I have my own personal opinions on these. I think the top 2 are meh. They're okay. You know, languages are to tell computers what to do, whatever. Modular development, I've seen incredibly large monolithic projects that steamroll in speed and deliver great quality, and microservice projects where nobody agrees and everybody separates into modular development teams and it all falls apart. I don't think that those are just super big wins. I think they're fine. But separate security domains, right? If I have important secure information on one system and not on another, I get to treat it differently in a microservice. I can build one service with different security requirements, different availability requirements and different resiliency requirements, which means that I don't have to solve the hard problems for all of my data. I get to solve the hard problems only for the data that needs hard problems solved. So in distributed systems, the problem is this, is that you look at a system, it is clearly completely broken, and all the systems are going, it's good, I've got everything, everything's aligned, I'm completely in sync with my peers, and they are not. So one of my favorite words in all of computing is pathology, which is not a computing term, it's a medical term. So the idea is that pathology is concerned with the diagnosis of issues with post-event analysis. Usually you're looking in a lab at blood or something like that to try to figure out why somebody died. In this case, we're looking at the artifacts of failure in systems, core dumps, broken system states, things like that, and we're trying to figure out what was wrong with the design. And then pathological, this is why I love this word, pathological liars, they're not people like fastidiously trying to figure out how to lie, right? It's a compulsion, right? So pathological, the word pathological also means obsessive or compulsive. So I find that distributed systems problems require a tremendous amount of research and understanding about the emergent state of the system, which is the first definition, and you have to be obsessive compulsive in order to enjoy it. So you have to be you have to have a pathological interest in pathology, which is fantastic. So you should read all of the articles that I linked. Again, the slide stack is here, which has all of the links to all of the articles. That'll give you a very good education and a way to think about distributed systems.